Hello, welcome to StatEase webinar, how to get started with Design Expert software. We will get started here today. We have about 128 people online right now. There'll probably be some more joining us in the next 5 or 10 minutes as people have a chance to download the GoToMeeting and get logged in. My name is Shari Kraber and I will be giving this presentation today. I assume that most of you are here because you are new to Design of Experiments or at least new to Design Expert software. And so the goal of this is really just to give you a very, very quick overview of some of the primary features of Design Expert software and some basics to Design of Experiments. If you have questions beyond the materials that are covered here today, we definitely welcome you to send them to us. And we'll give you some email addresses besides my own that you can feel free to send us questions today or whenever you are interested in doing some more work with the software or with DOE. So there are a lot of free resources available to you, specifically on the statease.com website. We have a page that is dedicated to beginner resources, and we have our webinar page where we have recordings of previous webinars, and we started recording the webinars just about 6 months ago, so there's only a couple of them recorded. Ones before that, the presentations are still available to download. And there's a lot of articles on the articles page, case studies, so you can search for ones that might pertain to what you are doing. And then there are also the tutorials. The software tutorials are really one of the very best resources to teach you how to use Design Expert and how to do DOE. They really talk you through how to get started with the software. So I encourage you to check out all of those resources. There are also other online resources, and ones that I'm most actively involved in are some of the LinkedIn groups. There's a LinkedIn group called The Design of Experiment, and then in parentheses, DOE group. This is filled with several hundred members, many of whom are experts in DOE, and anybody is welcome to post general questions about their DOE work and get some advice from this great group of resources. A lot of consultants and engineers, other people just like yourselves who are interested in DOE watch that and are happy to help answer questions. The ASQ Statistics Division has its own LinkedIn group. Offers a little bit more general statistics as well as DOE. And then the StatEase Professional Network is hosted by ourselves. And of course you are welcome to join any and all of those and use them as a great resource. So I'm going to start out by just talking about what is Design of Experiments and when can you use it. What industries can DOE be used in? We have applied DOE in so many industries, it's really phenomenal. Everywhere from the food industries to pharmaceutical industries to standard manufacturing to the military applications, NASA, car racing. It's really quite amazing. Basically, to do Design of Experiments, you need to have controllable factors, so some inputs that you can physically control, and some measurable responses, those quality characteristics that you are just always, as standard practice, measuring, monitoring, and making sure they are at their optimal levels. We are trying to create cause and effect relationships, establish cause and effect relationships between the control factors and those responses. And these have to happen above and beyond the noise that's going on in the process. So I am going to take 1 second here and just pause for a moment, and I will be right back. Okay, I'm back. We actually are not certain why that dinging keeps happening, so I just set a person about trying to figure out how to get that. So hopefully we'll get that dinging noise resolved and cleared up for you guys. It is not analyzing historical data. Design of experiments is different from just doing regular regression analysis. It is a point at which you have to actually control things and measure things. Take, for instance, the stock market. The stock market, we are always doing forecasting, maybe some time series analysis, those types of things, regression analysis on the stock market, but we cannot do a design of experiment on the stock market because we can't control the variables. And so that's really the key definition of what makes a designed experiment, is whether you can actually control the inputs or not. So we can do historical data analysis on many, many things, but a little bit more limiting to actually do a designed experiment. Experimentation is very iterative. It is unlikely that just one experiment will solve the complete problem, give you all the answers. But each experiment should give you many answers, and then it's up to you to decide if you want to do additional experimentation. We use subject matter knowledge, everything you know about the process, to bring all your theories, all your conjectures, all your knowledge about the system. We use that to help decide what kind of design we want to run. Do we want to run a 2-level factorial design in order to just estimate main effects and interactions? Or do we already know what the main factors are, and maybe we want to find an optimum region, and so we need some sort of response surface design? So the point of knowledge that you're at will dictate what type of design that you use. From there, you can go out and physically run the experiment. And of course, that's the easy part. There's never any problems running any of your experiments. You always get all your data nice and clean, just like the textbooks, right? Okay, so when you stop laughing, we know that there are things that go wrong during your experiment. Your machines shut down, you run out of raw material, various things happen. Operators switch your runs, they switch some levels on you. And so all of that messiness ends up going into the analysis. The key is, if you have a robust design to start with, good, solid, practical design to start with, then you can almost always get a decent analysis out. It won't necessarily be a textbook analysis, but it'll be a good analysis, enough that you've learned a bunch of things and can make some progress, make some good business decisions, and then continue on, like I said, into another experiment or moving on to another project. Because of the iterative nature of the experiments, we often suggest that people plan to only spend about 25% of their budget on your first go-round. Then do more, maybe 50% of your budget as you continue in your second round. And then always hold back a little bit of money so that you can do your confirmation runs. The traditional approach to experimentation is one factor at a time. Sometimes we call that OFAT, while we hold everything else constant. This is a simple approach, but it doesn't account for interactions. I am confident that most of you have a lot of years of experience in your job, in the processes that you're responsible for, and you already know those big factors, big variables that explain the process, that are responsible for changing the response positively or negatively. So one factor at a time type of experiments that we've done all these years has given us that information. The interactions are the things that your team might be arguing about. One person says, hey, I know that this factor affects the process because I saw it last week. I changed it and the quality characteristic changed accordingly. But another guy says, hey, yeah, but the week before that, I changed that same factor and it did nothing. If I hear that kind of disagreement among teams, I instantly think they're probably both right. But probably what's going on is, while there's another variable that's changing at the same time as the one that they think that they're studying. And so that is showing that there's possibly that there's interactions between the variables. As soon as you hit that stage of arguing whether factors are significant or not, or important or not, that's when you need to start thinking about design of experiments. Design of experiments allows you to study multiple factors at the same time, so it puts you into a parallel processing mode. We can look at many things. We can look at interactions between variables. It's a way of getting the most information out of the minimal number of runs. So I'm going to talk for a few minutes about the factorial planning process. And this planning process, planning is like absolutely the most critical stage of the whole design of experiments. If you don't have a good plan, there are just countless ways of making errors and choosing bad designs and stuff. So it all starts with planning. People like to send us lists of factors and simply say, okay, I want to study these 5 factors. What design should I choose? We can't answer that. That's not enough information. We have to go back and say, well, what are you trying to achieve? What opportunity is there? What is your objective? What are the responses that you're measuring? And what is your goal with those responses? So step number 1, write down what exactly you're trying to achieve, define your objective. Number 2 expands on that. So state the objective in terms of your responses. And that's broken down further. Okay, so the first part is figure out what change in your response that's important for you to find with this design experiment. So let's take yield, for example. If I'm currently operating at maybe an 80% yield, obviously the objective of any study that's studying yield is to maximize yield. But just saying maximize yield, that's not a clear enough goal. We want to say, okay, how much of a change in yield from our current condition would be enough to get us excited about the change that's being made in the process? If I could increase yield from 80% to 81%, is that going to get anybody interested in what I'm doing? I'm guessing probably not. So what is that minimal change that's important to find? Is it a 2% change, a 3% change, a 5% change? I don't know. So let's just say, for instance, that we're looking to detect a 5% change in yield. Okay, so that is what's called the signal that we're trying to detect. We want the design to be powerful enough to detect a 5% change in yield. All right, so 2B says estimate the experimental error or the standard deviation for that response, for yield. You can do this by looking at your historical data. You know, everybody has a quality database. They've measured these things forever. So go through that database and take a nice sample of data and pop it in Excel and get a standard deviation. That number should be a nice representative standard deviation of the process. So whatever you choose to put in there, it's not, I can't tell you what to do. It's just what you feel is a representative sample. Then you pair those, that signal divided by the noise, that gives you a ratio, and we can use that then to estimate the power of a design to detect effects. And so that's just one of the things that is newer in the setup of design of experiments versus if you were doing DOE even 10 or 15 years ago. This whole concept of sizing a factorial design really didn't exist back then. The third step, of course, is to put in your input factors and the ranges, the levels that you want to study. Those factor ranges will dictate how big of a change in the response that occurs. So for instance, our yield, if we have maybe some time and temperature changes, we have to make sure that those time and temperature settings are far enough apart that we would expect to see a change in the yield produced. So you can't have your factor levels so narrow that they're not going to do anything. You have to kind of push them out far enough that you will induce a change. That's the whole goal here, is to push for change. So given all this information, we then choose a design and do some things that we don't have time to go through much here. We look at something called aliasing. We would check out our power information, make sure that there's enough runs. And then we also always want to make sure that everything is safe, that all these factor settings are going to be able to produce meaningful data. This doesn't mean that it has to be saleable product, just means it has to be measurable product. I like to tell people that in order to figure out how to make good product, you have to understand how to make some bad product. So your design of experiments results, best case, is that they will span the whole range from some bad product that you would never let out the door all the way up to some great product that you'd love to sell. We're trying to figure out what changes the process so much that we can produce good versus bad things. Then in the future you'll know how to control that. There is a factorial planning worksheet, and this is available in the presentation that I've uploaded to our website, so you can get this. So this worksheet is just a great area for you to type in your whole objective, and it gives you a place to type in your response names and the change in the response that you're looking to detect and the standard deviation and the signal to noise ratio. Then it also gives you a spot to put your input factors and their ranges, their low and high levels. And then way down at the bottom is where you can start writing in like the design that you're going to choose. If you're going to choose to replicate things or put in blocks or center points, those are all kind of extra piled on top opportunities for you. So this worksheet is also in our handbook for experimenters, and our handbook is available free of charge for anybody who purchases the software and sends in the registration, just emails a registration. Then you'll be able to get one of these handbooks. So it's a nice guide. There's other worksheets and there's a lot of other tools in that handbook for experimenters as well. All right, so let's talk a little bit about choosing a design, and then we'll get into our popcorn experiment and show you Design Expert just a little bit. The opening screen of Design Expert looks something like this. Kind of made it a little smaller, but it across the top it shows the number of factors that you're studying. On the screen it says 2 to 8 factors. It actually is a much bigger matrix than that. And then along the side we've got the number of runs that are available. And there's a variety of different options. The 2-level factorial designs are all this color-coded screen that you see up front. And then I'll talk briefly about some of these others. We have some minimum run designs that are very appealing if you're trying to save some money. And irregular fractions are also a smaller number of runs. There are general factorial designs and optimal designs. These two options are for when you have differing number of levels. So usually we just talk about doing 2 levels for each factor, but the general factorial can handle doing like 3 or even 4 levels for the factors. And then Plackett-Berman and Taguchi designs are other options that we usually don't generally recommend. They're at the bottom of the list. So the designs at the top of the list would be our first choices. The help system, if you click on help, you will find some great hints, tips on everything. I've given you a screenshot here. In particular, I like this topic. There's an experimentation getting started topic that tells you gives you some questions. Where can I start? What type of objective you have, and given that objective, we give you some design recommendations. We talk a little bit about some different responses, talk about how to figure out the number of runs that you need with that power information. So there's a lot of information. There's also links to the tutorials right in the help system. So the tips button, the screen tips button, is a little light bulb that's in the software. You'll see that across the top there. There's a little light bulb, and you can click on that and get help that is specific to the screen that you're on. So that's really nice if you're going through some of the diagnostic plots and you don't remember what you're supposed to be looking for. You click on that light bulb and it'll just pop up some help for you instantly. So it's kind of on the fly. All right, so just talking first of all about the main regular fractional factorial designs. They are color-coded to help make it a little bit easier for you in a stoplight fashion, red, yellow, and green. So thinking about our interpretation of a stoplight, the red designs are stop and think. Probably stop and don't use them. They're very, very small designs, minimal number of runs, and when you're trying to detect your main effects, those main effects will actually be confused with your 2-factor interactions, so they will not be clean. Some people say to use these minimal resolution designs, resolution 3 designs, for detecting main effects, but that's actually kind of misleading, because if there are any significant interactions in your system, then they're going to be completely biasing the main effects estimates and confounding with them, confused with them, and can really mess up the analysis. So generally, we steer people away from those red designs. The yellow designs, the resolution 4 designs, you can kind of proceed with some caution in using them. You'll get clean main effects, and that's the cool thing about them. They're smaller number of runs, clean main effects. Your interactions might still be aliased with other interactions. They're a good choice for a screening design because of the alias structure that's with them. Resolution 5 designs are the green designs, and green means go fast. Use them freely. The white designs have absolutely no aliasing and can estimate all effects, but the problem with them is that they're like the maximum number of runs. They're every possible combination. And so they might spend more resources than you need to have. So I like to go back to the green designs usually half the number of runs, and still give you all your main effects and all of your two-factor interaction effects. So that's just a brief rundown. If you're new to DOE and not sure what design to use, my guidance is go for the green designs or the full factorials if you possibly can, and you kind of stay safe with those. The next two options on the opening screen are the minimum run designs, and these are resolution 5 or resolution 4 designs. Resolution 5 means it would be a green design. The green designs, again, can estimate all your main effects and your two-factor interactions. And then lower down the list are the min-run res 4, which would be considered yellow designs. So we have this little table just to give you some comparisons. Say, for instance, if you take 9 factors, in order to get all your main effects and two-factor interactions in a standard design, that would be 128 runs, which is probably way too much for most of you out there. So the alternative is a minimum run resolution 5 design, which can still give you all your main effects and all your two-factor interactions, but with only 46 runs. And that's a third of the price. So it's a fabulous savings, and you can get 9 factors in there. That's a lot of factors to study all at once. If you want to go smaller than that, you could just do a screening design and just be focusing on detecting your proper main effects. A standard design, yellow design, would be 32 runs, but the minimum run res 4 design has 18 runs as the base, although we always recommend adding 2, and the default of Design Expert will also add 2. So you would actually end up doing 20 runs for 9 factors. Still, I think a pretty reasonable price to pay to study that many factors. So the strategy of experimentation that we follow often is to start out with screening designs to kind of sift through your main factors and make sure that you're just focusing on the things that are really significant. Using the Resolution 4 yellow designs is a great choice. The Resolution 5 green designs are great for characterization when you really want to understand your main effects and interactions, and at that point start putting in some center points to find out if there's any non-linearity in the process. Find out if something more than just a straight line occurs, if you need a quadratic or higher order polynomial to represent all the functions that are going on. And the response surface designs, which is a whole other tab, things like central composite designs or optimal designs are available once you've screened down to just the vital few factors and you know that you have some curvature, some nonlinearity. So those are just basic choices for you. The last step is always to do some confirmation, some final runs to just make sure that the results of the DOE are as you expect them to be. All right, so now I'm going to take about the next half hour or so to run through a basic analysis. And this case study is taken from our Experiment Design Made Easy workshop. For more information on that workshop, you can follow this link. In the presentation that I've uploaded that you can print out, I have put in all the slides so that you can go through this on your own. You can download a trial version of Design Expert, and every single slide is in there so that you can build this design and go through the analysis and kind of duplicate everything that's in there. So there's a lot of slides in here that I will not be going through during this webinar. So it's kind of there for your own self-study. I wanted to make sure that I provided you with that ability so that you could go through this on your own. after I'm done. So our little example is about investigating how to pop some great microwave popcorn. And we're going to study 3 factors here. The brand of popcorn, using a generic brand popcorn versus a name brand popcorn. And we're wondering, is there a difference between these types of popcorn in the flavor, the quality of the taste, and in the amount of unpopped kernels that get left in the bottom of the bag also. We're going to compare the time in the microwave and the power setting that's used in the microwave. Of course, I mean, these days we just have that popcorn button that we press, and then we always get a perfect bag of popcorn. But this design was done back in the early 90s, and microwaves weren't quite as sophisticated back then, and so we had to control it just a little bit more by hand. This screen shows the factor settings, the runs that were done, and the taste and the unpopped kernels, the amount of unpopped popcorn that was left in the bottom of the bag. And so, for instance, the first run used the expensive popcorn, that name brand popcorn. We put it in the microwave for 4 minutes at 75% power. And when we came out, we gave all these bags of popcorn to some expert panelists to rate the taste. Okay, it was actually probably some neighborhood kids that came in to get some free food, but we made them rate all the bags of popcorn that they tasted for us. So as a group, the average rating was a 75 on the taste, and then we measured the amount of unpopped kernels, and we had 3.5 ounces of unpopped kernels at the end. And so on. So we did all 8 combinations here, rated all of these, and measured them. And now we want to do the data analysis and find out, is there actually a difference between the brands? Did the time or the power settings affect either the taste or the unpopped kernel amounts? So I am going to, at this point, switch over to Design Expert software and walk through building this. And as I said, if you've got the presentation in front of you, you can kind of follow along in that. Otherwise, you'll just be following along in the with Design Expert or watching me do this. Okay, so this is the opening screen of Design Expert. We had 3 factors and 8 runs, so we're selecting this 2 to the 3rd factorial design. And I'm going to go over to the bottom right-hand corner and click Continue. Oh, and I get a little warning message. It says, hey, this is a really small design. Effects must be at least 2 to 3 times bigger than the noise in order to be even detected with this design. Check your power. Do you want to continue? So this is just your little warning with any 8-run design that we give you to remind you that these are small designs and your effects have to be quite large in order for this design to even find them. So I know this. I'm going to say yes. I'm going to continue. Then I would type in all of my factor information. Brand is a categoric factor, so I changed it from numeric to categoric. And I have cheap and costly as the levels. And then I have the 2 responses. And I build the design. And the design will come up in a random order. If you don't like the order that it came up in, like, this is not actually a very good random order, to be honest, because I have all these 100s all together here, and that shouldn't happen. So I'm actually going to re-randomize this by right-clicking on that. I'm going to randomize and just say all and see what it does for me. Oh, then I have to sort. I have to sort by the run order. Oh, that's even better. Now I have all the 75s and all the 100s together. Yeah, there we go. That's a little bit better. So I have 75, 100, a few more 75s, a few more 100s. There's not a whole lot you can do with randomization in an 8-run design, but in general you should have the levels mixed up as much as you can. Okay. I'll pull up the file with all the data in it. Here we go. And then we'll walk through the analysis. So over on the left-hand side, there's a word called analysis. Right below that, we list all the responses. I'm going to click on the word taste. And I get my button, my analysis buttons. We normally just skip over the transformation button. It can be used later if we want to. And we start on the effects button. The effects graph is, I'm sure, a new one for you. It lists or shows graphically the size of the effects from smallest to largest. So if you look at the x-axis is going from a low on the left side of 0 all the way over on the right side to 21.5. If we're trying to determine which effects are the biggest effects, we're going to be looking for the ones that are over on the right side of this graph, because the right would be the largest, and they're most likely to be statistically significant. So I'm going to start from the right, and I'm going to click on here. And basically, by clicking on these, we turn them on. And when we say we turn them on, that means we're putting them into the analysis of variance. And these 3 terms are the biggest ones. So I'm going to turn those 3 on, and then all the rest of these over on the left side are the little ones, and we're going to leave those. They are going to be pooled together and be the error for all of our testing that we do in the ANOVA. So the use of the half normal plot is a little bit of an art. It just takes a little bit of practice. There's a couple responses here that you can practice with, but it's a really great graphical tool to determine how to split your effects in half. The ones on the right will be significant. The ones on the left will not be significant. And you look for a nice gap between the significant and insignificant ones, and some various other things that you learn as you go along. One other thing, useful tool, is the Pareto chart. It's another way of representing your effects. This is great for managers who maybe don't understand that half normal plot, and kind of visually helps them see the big effects versus the smaller ones. So I'm going to go back to that half normal, and then I'm going to continue on onto the ANOVA button. The ANOVA, when you first look at it, has all this annotation on, which kind of explains what a lot of the stuff is. This stuff scares people. But what I can tell you is all the stuff on the left is just the math required to get this one final column that we actually look at. The p-value column is really the only column that you need to be focusing on. It tells you if these terms are statistically significant or not, and we even give you some extra guidance here. Generally, if p-values are less than 0.05, that's a standard rule that we would say it's statistically significant. And usually if p-values are greater than 0.1, we'll say they're not statistically significant. Those are just general guidelines, and that's what's followed down here in the blue text. And so I can see that, hey, my time, factor B, was significant, power was significant, and the interaction between those two things was significant. Now, what I can see right away that's interesting here is that the thing that is not significant is our third factor. It was brand. So evidently, there's no significant difference between the taste of the name brand versus the grocery store generic brand. So you've already got a conclusion right away. At this point, we would normally go through all the diagnostics That is all in the materials that I've provided for you, so I'm not going to go through those right now, but I want to get to the model graphs and take a look at the information that's in here. These interaction graphs are new to most people. They are attempting to show three things in a two-dimensional space, and so that can be a little bit tricky. We have taste, which is our response on the left-hand side on our y-axis. So taste is going from 30 to 90 here. If you remember, we were trying to maximize taste. And time is on the x-axis, so we're going from 4 to 6 minutes. The interesting part is that power is being represented by these two lines, the red line and the black line. The low power is the black line, the 75% power, and the red line is 100% power. So if I were to pick any particular corner here, like let's take this one down in the lower right-hand side, and I can click on it and actually kind of turn it on, and it displays the settings and the legend. So I can say, hey, that's 6 minutes time, 100% power. And I can see that the rating, the taste rating, was a 37. Now what do you think of that? 37. That's a pretty low taste rating on a scale of 1 to 100. And so we're 6 minutes at 100% power. Probably we burned this popcorn. Probably is not a very flavorful popcorn. That burnt taste, these taste testers didn't really appreciate that, and so they gave it a very low rating. Now, up in some of these other corners, but just going up from that one, we have 6 minutes at 75% power gives us a taste rating of 75.5. So that's very good and is acceptable. So you can keep the popcorn in the microwave for the 6 minutes, but at a lower power setting. On the back to the left side of the graph, there's a couple other options. You can use 4 minutes of time and either 75% or 100% power gives you very similar taste results. So similar, in fact, that we have this other scaling. If you notice, there's these black and red, like box and whiskers kind of bars. They're called LSD bars, least significant difference bars. And this is explained in the help system if you want more detail on that. But basically, that is an interval in which the mean could float. If you did the same design again, the mean might kind of float up and down within that interval. And if two LSD bars are overlapping, that means the results are statistically the same. So, for instance, the LSD bar in the lower right corner, the red one here, and any of the other LSD bars are not overlapping. So that would tell me that they are statistically different results. And on the other hand, the three at the top are all overlapping, and so they are all basically the same result. So I couldn't say, I don't have confidence to say right now that this red triangle up here is the best setting. It's statistically, with this data, with these 8 runs of data, it is not any different from either of these other two settings. You'd have to collect more data and see if you could really declare that as better. The only one I can say is really different is the one in the lower right-hand corner, which is definitely the worst. There are other ways of viewing this. They're rather fun, and you might get into. There are contour plots. So over on the Graphs tool on the left, I just clicked on Contour, and it gives you a different viewing. The two factors are now on the X and Y axis, and the response, taste, is shown as a series of contour lines that go from low, which is blue, up to high, which is the red. And so we are trying to find settings, that are good. Anywhere in the more orange or red area would be acceptable, and we want to avoid that top right corner. There's also the 3D surface, which can be turned around and is, just a 3D depiction of that contour plot. So there's a lot of fun visual tools available. They are all giving you the same information. You can find the one that means the most to you for a particular design and use that, but they're all giving you the same information. For factorial designs, we usually stay with the default of the interaction graphs. When you go to response surface designs and you have more and more curvature in the surface, then you'll go to probably the contour or the 3D surface graphs. So there is a second response to analyze the unpopped kernels. I'm going to let you do that analysis on your own. I'm going to flip back to the PowerPoint slides. And so you can analyze the unpopped kernels on your own, and then ultimately you want to pick time and power settings that maximize the popcorn taste while minimizing the unpopped kernels. And these are the two final graphics that you get. The one on the left is the one we just looked at for the taste, and the one on the right is the unpopped kernels. Turns out time and power are also the two big factors in determining how much yield you get. And with unpopped kernels, you want to minimize those. So probably something along that 100% power, that red line along the bottom, would be the ideal. If you go to the lowest one, which isn't statistically different from the second lowest, but people do tend to kind of gravitate towards either lowest or highest. If you look at that, it's the 6-minute 100% power setting. So although it gives you the least or the fewest unpopped kernels, we also got the burned popcorn there. So it's probably not an overall optimum. It's maybe the optimum for unpopped kernels by itself, but it looks like we're going to have to do some compromising. And that's what is usually required with most real-world applications, is that we have to compromise in our responses. And so perhaps the second best unpopped kernels, the one at 4 minutes and 100% power, is the optimal setting, as that also produces a nice high taste value. Okay, so that completes a little run-through of Design Expert. I just kind of wanted to briefly show that to you. I wanted to finish up with just a few keys to good experimentation, typical things that people new to DOE need to watch out for. So we'll go through these one by one. These are excerpted from an article that is posted on our website. So the link is there, and you can download that if you would like. So the first key is going back to that planning process. Establish a clear purpose for your experiment. Why are you doing it? What data will you collect? How is it going to help you improve quality, reduce costs, decrease cycle time, things like that. You can't just say, well, I'm going to run a DOE on this process. You need objectives, because that helps you determine what type of design you want to run. You need to invest in the response measurements. Those responses need to be numeric, quantitative. The statistical analysis requires numbers. We can't analyze text very well. So if you currently say something is either a pass or a fail, well, you're going to need to turn that into a number somehow. The more precise you can measure something, the better. That will provide power, which will reduce the number of runs that you need. There's an option. You can do repeated testing if your measurement system isn't very accurate. You could measure something 3 times and put in the average, and that will increase your power. Accuracy is great, but as long as you're consistent, then your data collection should be okay. So consistency is even more important. So ideally you have continuous numeric data. That's better than just counting data, and that's even better than pass-fail data. If you really do have pass-fail data, maybe you can put it into a rating scale, such as a 1 to 5 rating. And rating scales work very, very well for data analysis. Just make sure the scale is big enough and people are trained in how to use it so that you get consistent scores when you're doing your ratings. So invest in your measurement in order to have good data analysis results. Assess the power of your design. Get a good estimate of the standard deviation of each of your responses. You can use historical data. You can use control charts. You might be doing a process capability study. You can look at the data from a prior experiment that's been done. Or one of the options that I use very frequently is a SWAG, which is, in my terms, it's a scientific wild-ass guess. Just a reasonable guess as to what the standard deviation is. It doesn't have to be perfect, just a decent guess. Then decide within your team environment, decide on what the change in the response is that you want to detect. So it's the minimal change that you're willing to detect. If your boss says, hey, I want you to find any change in, say, yield, then you have to go back to them and say, yes, but in order to detect any change, even a minute change, that's going to take me hundreds or thousands of runs. Then he'll back off a little bit and say, well, okay, what if we could detect a change of 2% or something like that? And I didn't show you it in the software, but it's easy enough to find. You can confirm that your design has enough runs for adequate power, so you want your power always to be about 80% or higher. And power is shown in the tutorials and in the help system if you want to look it up and get some more information. Randomize the runs. You want to make sure that you kind of protect yourself from anything going on during the course of the experiment, such as your temperature or humidity conditions changing, people getting worn out, machine wear, chemical degradation, things like that. Never run all low and then all high. And if your random order comes out, as mine did, with all the lows and all the highs grouped together, then simply re-randomize. And there are multiple ways to randomize the runs. Try to get a decent one. George Box wrote up an article about why must we randomize our experiments, and that reference is given to you on the bottom of this page. We didn't talk about aliasing very much here, but it's really, really one of the keys to understanding the design choice that you make. It's a problem that comes with any fractional factorial design. As long as you can afford it, use the green designs, which are resolution 5 or higher. Those will put yourself in a situation where you don't have to worry about the aliasing. The yellow designs, resolution 4, they're okay for screening. They will give you your main effects. and you'll just have some messiness in the interactions that you might have to clean up further. And as it says, do these when you can do a follow-up experiment if needed to figure out which of the interactions are truly significant. The resolution 3, the red ones, are dangerous because the main effects are confounded with the two-factor interactions. So they're not really giving you clean estimates of anything. We want you to not try to run one huge design experiment all at once. There's too many mistakes that can happen, too many things that can go wrong if you run one huge experiment. It's really better in most cases to run smaller groupings of experiments. If you can, do some screening first, figure out what factors are actually important, and then go on to the characterization designs and even add center points to test for curvature. Then finally you can do response surface designs if you want to. And lastly, and this is a step that it's amazing how many people just don't do, confirm your results. People will send us a data analysis and say, does this look right? Well, all we can do from a statistics side is see if the data that you collected fits the model. But you have to go out and do the confirmation studies to see if this model holds true in the future. And so hopefully it does, but don't assume it. There's prediction intervals that are presented in Design Expert to help you have a range in which you would expect to find results. And don't expect miracles. Stuff's still going to continue to happen, but the design of experiments should help you gain a lot of process and product understanding that will really help guide you in the future and hopefully enable you to troubleshoot your processes much better. As one additional reference that you might want to take advantage of is the textbooks that Statis publishes, DOE Simplified and RSM Simplified. These are just great to walk you through the basics of either factorial design or response surface design, and these are available for purchase on our website, and they are funny. They are very entertaining. Mark's done a fabulous job of throwing in a great sense of humor along with Pat's fabulous ability to bring all of these tools and techniques down to a level that anybody can read and understand. So they're not going to explain the theory to you. You're going to have to go to some college textbook in order to get the theory, but these are the practical applications of how to use DOE in the real world applications. So with that, I think Wayne has still been busy answering many of your questions. I'm going to call an end to this webinar here. We will stay online for another half hour or so, as long as it takes to answer questions. So we will be typing back and forth to individuals and helping you out. You can download a 45-day trial of Design Expert if you don't have it already from our website. And again, you can get a copy of this webinar on our website also. It is already posted there, so you're welcome to do that. I will also post a recording of this session, and so you can share it with friends, colleagues. It'll be there for years to come, so you can come back and listen again if you would like to. We have our DOE FAQ alert. If you are interested in more webinar announcements, you can subscribe to that following the link that's shown at the bottom of this screen here. So with that, I would like to say thank you for attending. It's been a great hour with you, and good luck for all of your experimentation. Please let us know if you have any questions. You're welcome to send emails to stathelp@statease.com. I see that that's not on this page. Maybe Wayne can type it in and send it to all of you, but it is stathelp help@statease.com, and we are more than happy to answer questions and talk to you more about any of this. So thank you very much for your attendance and listening. Bye-bye.